All right, so today we're going to jump into a really cool problem from I.E. Irodov's legendary physics book, Problem 1.170. Now, on the surface, it looks like your standard collision problem, but trust me, it has this fantastic little twist that really forces you to think about what energy and momentum are actually doing during an impact. Let's break it down together. So, before we even touch a single equation, let's just think about this for a second. When two billiard balls collide, what is really happening in that split second? It's not just an instantaneous boink. There's this moment of compression, a squeeze, where the balls actually deform a tiny bit. And in that moment, the energy of the system is doing something pretty incredible.
Okay, so here's the problem itself, straight from the book. We've got two identical balls. That means same mass, which is helpful. One is moving, one is sitting still. It comes in and hits the stationary one at an angle of 45 degrees. And here's the kicker. The question isn't about what happens after the collision. It's asking about the energy that's stored as potential energy right at the peak of that squeeze. That's the puzzle we need to solve.
To crack this nut, or really any collision problem, we've got to pull out our main physics tools. There are two fundamental laws that are going to be our best friends here, and getting them straight is absolutely key. First up, good old conservation of momentum. You know this one. It just says that in a closed system, the total amount of motion stays the same. The momentum of our two balls right before impact has to equal the total momentum right after. But here's the part you can't forget. Momentum is a vector. It has direction. And that little detail is going to be incredibly important for us. Next up is conservation of energy. And this is where people trip up. You've probably heard that in an elastic collision, kinetic energy is conserved, right? Well, that's true, but only if you compare the moment before the collision to the moment after. The magic, the thing this whole problem is about, happens during that moment of impact. At the peak of that squeeze, some of that kinetic energy isn't kinetic anymore. It's been temporarily transformed into elastic potential energy.
Okay, so we've got this 2D collision, which can feel complicated. Trying to solve it all at once is just messy. The secret, the real pro move here, is to break the problem down into simpler, one-dimensional chunks. And we do that by picking a really smart axis to work with.
And this is how we do it. We define something called the line of impact. It's super simple, really. Just a straight line connecting the centers of the two balls at the exact moment they touch. Then, we take the velocity of that incoming ball and break it into two pieces, or components. One that runs parallel to our line of impact and one that's perpendicular to it.
Now, you might be asking, why is that so helpful? Well, the problem gives us a huge clue. The balls are smooth. And in physics, smooth is just a code word for frictionless. That means there are no forces pushing or pulling perpendicular to our line of impact. So that perpendicular part of the velocity, it just cruises on by, totally unchanged. All the action, the force, the squeeze, the energy transfer, it all happens only along that line of impact. And just like that, we've turned a messy 2D problem into a simple 1D problem.
All right, so this brings us right to the core of the problem, that one special instant of maximum deformation. What's actually going on physically in that moment?
So what does maximum deformation actually mean? It's that tiny instant where the balls have stopped getting closer, they're as squished as they're going to get, and they're just about to spring back. And for that single moment, what does that imply? It means their speed along the line of impact is exactly the same. They are, for just a moment, moving as one cohesive unit along that axis. This is the big aha moment right here. Let's just lay this out so it's super clear. Before anything happens, all the energy in the system is kinetic energy, and it all belongs to that one moving ball. Potential energy is zero. But right at that moment of maximum squeeze, the game has changed. The system still has kinetic energy, for sure. The balls are still moving. But now, a chunk of that initial energy has been converted into potential energy, stored in the compressed material of the balls. Our whole mission is to figure out just how big that chunk is.
Okay, deep breath. We've handled the physics concepts, which is honestly the hard part. Now we can walk through the math. And trust me, because we set it up so nicely by choosing our axis, the math becomes way more manageable than you'd think.
So here's our game plan, step by step. First, we'll pin down the total initial energy. Second, we'll use momentum conservation to find that shared velocity at the moment of the squeeze. Third, we'll calculate the kinetic energy at that exact moment. And finally, the difference between the start and that middle point will give us the potential energy. Let's do it.
Step 1. Let's look at where we start. The total kinetic energy in the whole system? It's just the energy of that first ball. You know the formula, 1/2 mv². And the part of that velocity that's actually doing the work in the collision, the component along our line of impact, is just v times the cosine of our 45-degree angle.
Okay, now for step 2. We're going to use conservation of momentum, but, and this is the key, only along our special line of impact. Before the hit, the momentum along that line is just the ball's mass, m, times its parallel velocity. At the moment of max deformation, the two balls are moving together, a combined mass of 2m with some new shared velocity we can call v common. We set those equal, the m's cancel, and we find that this common velocity is just exactly half of the initial parallel velocity. Simple.
All right, step 3. Let's figure out the total kinetic energy right at that instant of maximum squeeze. Now remember, it's got two different pieces we have to add together. First, there's the kinetic energy from that perpendicular velocity component of the first ball, the part that didn't change at all. And second, we add the kinetic energy of the combined two-ball system moving along the line of impact with that common velocity we just found.
So if the kinetic energy at maximum squeeze is less than the initial kinetic energy, where did that energy go? It didn't just disappear, right? Nope, it got turned into potential energy. To find it, all we have to do is subtract the kinetic energy at max deformation from the total kinetic energy we started with. The law of conservation of energy guarantees that this missing amount is exactly what was stored.
We are so close. The question wants the fraction of the initial energy that got converted. So all we do is take that potential energy we just found and divide it by the initial kinetic energy. And look what happens. When you write it all out, all the messy stuff, the m and the v, they all cancel out, leaving us with this really elegant little formula. The fraction is just 1/2 times the cosine squared of the impact angle.
So let's plug in the numbers. The cosine of 45 degrees is 1 over the square root of 2. You square that, you get 1/2. Multiply that by the 1/2 already in our formula, and you get 1/4, 0.25. That's our answer. Exactly 25% of the initial kinetic energy gets temporarily stored as potential energy at the moment of the big squeeze.
Okay, before we finish, let's talk about the common traps on a problem like this. The number one mistake is just assuming kinetic energy is conserved the whole time. It's not. The second is trying to use momentum conservation in 2D without breaking it down into components. Another big one is not really understanding that maximum deformation is the key that tells you the velocities are equal along the line of impact. Keep these in mind, and you'll be set.
And I'll leave you with a little something to chew on. We built this whole solution on one key assumption. The balls are smooth. But what if they weren't? What if there was friction between them? How would that change everything? All of a sudden, you'd have a force that could cause the balls to start spinning. How does that affect the energy? That's a whole new puzzle. Thanks for diving into this one with me.